Professor Belfrost's computer science class is back!
Okay, so welcome back to my class. So, yeah, uh, you will have the next lesson on CPU. I mean, not next lesson. I mean, just a continuation from the leftover part of our last lesson on micro programming, right? Okay, so here are a bit of recap for you to refresh. Okay, so for a control unit to perform its function must have inputs that allow it to determine the state of the system and outputs that allow it to control the behavior of the system. Okay, so inputs are clock, IR, flags, and control signals. Control unit can be implemented using hardwire and microprogram implementation. In a hardwire implementation, then the control unit is essentially a state machine circuit, and its input logic signal transformed into a set of output logic signals, which are the control signals. Okay. To simplify the control unit logic, then there should be a unique logic input for each output. And this function can be performed by a decoder which takes an encoded input and produces a signal. We'll discuss decoder further in this lesson, okay? And the term microprogram was first coined by Mr. Oster and Vivelkus in early 1950s. Okay, so each microoperation is described in a symbolic notation called microprogramming language, and each line describes a set of microoperations occurring at one time and is known as microinstruction. Sequence of instructions known as firmware or micro. So let's discuss review about the last lesson of microprogram microinstruction. So now we want to see actually how this working. So consider that for each microoperation, all the control unit is allowed to do is generate a set of control signals. Okay. So actually, its control line emanate from the control unit is either on or off, and can be represented as bit that each will represent one control line. And this must be different patterns of ones and zeros in the control word. Suppose we string together the sequence of control words to represent the sequence of microoperation performed by the control unit. Then we must recognize then the sequence is not fixed. Sometimes it can have a direct cycle, sometimes it's not. So what we need to do is having a unique address and add this address field to each control word, indicating the location of the next control word to be executed in certain condition. Also, we must add a few bits to specify the condition. The result is what called a horizontal microinstruction, which is the first type. Okay, and the form of microinstruction or control word is as follows. There is one bit for its internal processor control line and one bit for its system bus control line. Okay, there's a condition field indicating condition under which there should be a branch, and there's a field with the address of the microinstruction to be executed next when a branch is taken. And such microinstruction can be represented as follows. Okay, so to execute this microinstruction, just turn on all the control lines. Okay, and if the condition indicated by condition bit is false, then execute the next microinstruction in sequence. But if the bit is true, then the next microinstruction to be executed is indicated in the address field. Okay, so here the following figure that show the control words or microinstruction arrangement in a control memory. So the microinstruction needs routine are to be executed sequentially, as we have known, and each routine ends with a branch or jump instruction indicating where to go next. Okay. The control memory of the previous figure, which was on the previous slide, is a concise description of the complete operation of the control unit, which defines the sequence of microoperation to be performed during each cycle. But yeah, if nothing else, this notation would be a useful device for documenting the functioning of a control unit for a particular computer, and also a way of implementing the control unit. The control memory, also shown in the previous figure, contains a program that describes the behavior of the control unit, and it could be implemented the control unit by simply executing the program. And here's figure on the next slide that will show you the key elements of such implementation on the Okay, we have sequencing logic, control address register, control memory, control buffer register. Please pay attention to the arrow. Okay, the set of microinstructions is stored in the control memory, and the control address register contains the address of the next microinstruction to be read, and microinstruction is read from the control memory is transferred to the control buffer register. The left-hand portion of that register connects to the control lines emanating from the control unit and reading a microinstruction from the control memory, which is the same as executing that microinstruction. The third element is the sequencing unit that loads the control address register and uses a read command. And let us examine this structure with a greater detail. So comparing this with the next figure, you can see that control unit still has the same inputs and outputs. Here the next figure indicates but control unit function. We will describe it further. First one is to execute an instruction. The sequencing logic unit uses a read command to the control memory. The word whose address is specified in the control address register is read into the control buffer register. Next is the content of the control buffer register generates control signals and next address information for the sequencing logic unit. Okay, please uh, follow me by following also the diagram shown. And the fourth step, the last step is that sequencing logic unit loads a new address into the control address register based on the next address information from the control buffer register and the ALU flag. And all of these four steps happen during one clock pulse. The last step, just the state need elaboration and the conclusion of each and at the conclusion of each micro instruction, then the sequencing logic unit loads a new address into the control address register. Depending on the value of the ALU flags and the control buffer register, one of three decisions is made: to get the next instruction, to jump to a new routine, or to jump to a machine instruction routine. Okay. The previous figure shows two module level decoder. You can see upper decoder translates the opcode of the IO into a control memory address, whereas the lower decoder is not used for horizontal micro instruction, but it will be used in vertical micro instruction. The horizontal micro instruction every bit in the control field attached to a control line, while in a vertical micro instruction, a code is used for each action to be performed. And here the advantage of vertical micro instruction over the horizontal, which is actually they are more compact. We need fewer bits than horizontal micro instruction, and the expense of small additional amount of logic and also the time delay. Okay, so this is very, very, very important. Okay, so Wilkes first proposed the use of microprogram control unit in 1951, and actually this subsequently elaborated into a more detailed design. And here is the configuration proposed by Sir Wilkes. Okay, so actually you can see it. The hard disk system is a matrix, okay, partially filled with diodes. And during machine cycle, one row of the matrix activated with a pulse, and this generates signals of the points where diode present. The first part, the row generates the control signals that control operation of the processor. The second part will generate the address of the row to be pulsed in next machine cycle. With the beginning of each cycle, and the address of the row to be pulsed is contained in register 1. And then depending on the control signals, either the opcode in the instruction register or the second part of the pulse row is passed into register 2 during the cycle. Register 2 is said to be gated to register 1 by a clock pulse. And this two register arrangement is needed because the decoder is simply a combinatorial circuit with only one register. The output will become the input during a cycle, causing an unstable condition. We will see this later. Okay, on the discussion on flip-flop and any other arrangement of combinatorial and sequential circuits. Okay. So actually, this scheme is very similar to the horizontal microprogramming, which is described earlier. But the main difference here, in the previous description, the control address register could be incremented by 1 to get the next address. Whereas in the previous scheme, the next address is contained in micro instruction. To permit branching, a row must contain two address ports controlled by a conditional signal or flag. Okay, and yeah, the processor of the hypothetical machine includes of the Wilkes architecture includes the following registers. First is multiplicand. Second is accumulator of the LSH. The third is the accumulator of the MSH, and the fourth is the shift register. In addition, there are also three registers and two 1-bit flags accessible only to the control unit, uh, which one serve as both memory, MAR, and temporary storage. The second one is a PC, and the third one is temporary register, which used for counting. Okay, so actually there are 38 micro instructions that are required to define the system completely in this kind of architecture. Okay, the principal advantage of the use of microprogramming is actually to implement a control unit in a more simplified design. Okay, thus it is much more cheaper, and also it is less error prone to be implemented. Whereas a hardware control unit must contain complex logic for sequencing, and this is yeah, it needs many microoperations of the instruction cycle. On the other hand, the decoders and sequencing logic units of microprogram control unit are very simple pieces of logic. So this is the advantage of microprogram over the hardwire. Okay, but here's the disadvantage too. You need to consider. The disadvantage is that it will be somewhat slower than hardware unit of comparable technology. Yeah, but despite this, microprogramming is the dominant technique for implementing control units in PCIe architecture due to its case of implementation. RISC and processor with their simpler instruction format typically use hardware. Okay, now let us examine this approach in greater detail. So there's actually two basic tasks performed by microprogram control unit, which is microinstruction sequencing and microinstruction execution. In designing control unit, these tasks must be considered together because both affect the format of the microinstruction and the timing of the control unit. But there are two concerns which is involved in implementing this technique. This is the size of the microinstruction and the address generation time. The first concept is to minimize the size of the control memory reduces the cost of the component. And the second concern is actually simply a desire to execute microinstructions as fast as possible. So in executing a microprogram, then the areas of the next microinstruction to be executed is in one of these categories. First is determined by instruction register, second is the next sequential address, and the third is branch. Okay. The first category occurs only once per instruction cycle. Okay. The second category is the most common in most design, but this design cannot be optimized just for sequential access. Whereas the third one, branch, both conditional and unconditional are necessary part of a microprogram. Okay, so actually it's important to design a compact, time-efficient technique for micro-instruction branching. Based on the current microinstruction condition flag and the content of the instruction register, a control memory address must be generated for the next microinstruction. So there are a wide variety of techniques that can be used. Yeah, you can use two address field, single address field, and variable format, as shown in the figures A, B, C respectively. So the simplest approach to provide two address field in each microinstruction. A multiplexer provided that serves as a destination for both address fields plus the instruction registers. Okay, so here we have concept of control address register, which is subsequently decoded to produce the next microinstruction address. Okay, and the address selection signals are provided by a branch logic module whose input consists of control unit flags plus bits from the control portion of the microinstruction. Though this is simple, actually it requires more bits in the microinstruction than other approaches. Actually, we can do some saving by adding some logic, and the common approach is a single address field, which is shown in the second figure. While the option of the next address are as follows: first is address field, second is structure register code, and third is next sequential address. The address selection signal. determine which option is to be selected, and this will reduce the number of address built to one. But actually, this is not will this often not be used because there is some inefficiency in the microinstruction coding scheme. Another approach is to provide for two entirely different microinstruction formats. Okay, this is the third figure, and one bit designates which format is being used. In one format, the remaining bits are used to activate control signal. In the other format, some bits drive the branch logic module, and the remaining bits provide the address. Okay, with the first format, the next address is either the next sequential address or an address derived from the instruction register. With the second format, either a conditional or unconditional branch is being specified. One of the advantage of this approach is that one entire cycle is consumed with each branch micro instruction. Okay, so we have looked at the sequencing problem, and now let's review it of format consideration and general logic requirement. Okay, so another few points to consider the various ways in which the next address can be derived or computed. So here's the table that you need to consider. Okay, so it's divided into explicit techniques in which the address is explicitly available in the micro instruction, and implicit techniques which require additional logic to generate the address. Okay, so we have essentially dealt with the explicit techniques. Okay, trivial, unconditional, and conditional branch. So actually, with a two-view approach, then two alternative addresses are available with each micro instruction using a single address or a variable format. And first branch instruction also can be implemented. A conditional branch instruction depends on the following types of information: ALU flags, part of the opcode or address mode field, part of the selected register, and status bits within the control unit. Okay, now implicit techniques. So implicit, there are some implicit techniques. Okay, one of these mapping, which is required with virtually all design, and the opcode portion of machine instruction must be mapped into a microinstruction address. Okay, so this occurs only once per instruction. Common implicit techniques one that involve combining or adding two portions of an address to form the complete address. The final approach listed in previous table is termed residual control, which involves the use of a microinstruction address that has previously been saved in temporary storage within the control unit. Microinstruction cycle is the basic event on a microprogram processor. Each cycle is really made up of two words, fetch and execute. The fetch portion is determined by the generation of a microinstruction address, and this was dealt in the preceding section. And the section actually deal with execution of microinstruction. Let's see. So recall that the effect of the execution of microinstruction is to generate control signals. Some of these signals control points internal to the processor. The remaining signals go through the external control bus or other external interface. So the preceding description actually suggests the organization shown as in the slide. Okay, so in the slide, take a screenshot if it's necessary. Actually, this emphasizes the focus of this section. So the major module in this diagram should by now be clear. The sequencing logic module contains the logic to perform the function discussed in the preceding section, which generate the address of the next microinstruction using an input, the instruction register, ALU flags, the control address register, and the control buffer register. Okay, the control logic module generate control signal as a function and some of the bits in the micro instruction. Okay, micro instructions can be classified in a variety of ways, and distinctions that are commonly made in the literature including the following: vertical horizontal, pack unpack, hard soft, microprogramming, direct indirect, and coding. All these bear the format on the micro instruction. None of these terms have been used in a consistent, precise way. However, let's see some of the suggestion on some literatures. In the original proposal by Wilkes, each bit of a microinstruction either directly produce a control signal or directly produce one bit of the next address. Okay, actually this scheme requires a more complex sequential logic module. A similar sort of trade-off exists for the portion of the microinstruction concerned with control signals. By encoding the control information, subsequently decoding it to produce control signals, then the control what bits can be saved. Actually, how can this encoding be done? Okay, so actually encoding is quite a complex thing. So I want you to pay attention to the description give this. I'll not read it for you. I want you to take screenshot or pause the video and understand it by yourself. Okay. Okay. So yeah, we have done with the encoding part. So here are some degree of encoding spectrum that is very important. So please pay attention to the second pair of items in the table. So we have unpack pack. So encoding is done in such a way to aggregate function or resources so that the microprogramming is viewing the processor at a higher and less detailed level. Again, it should be clear that the task of understanding or orchestrating the use of all the control signals is different one. Okay, as mentioned, one of the consequences of encoding typically is to prevent the use of certain otherwise allowable combination. Okay, and yeah, as more complex and more aggregated encoding schemes are used, so more complex decode logic is needed, and this is in turn may affect performance. More time is needed to propagate signals through the gates of the more complex control logic model, and also the execution of encoded microinstruction takes longer than the execution of the unencoded one, and this should be taken as consideration. That's all of the characteristics listed in the previous table for a long spectrum of design strategies. Okay, design toward the right end are more concerned with optimizing the process of microprogramming. And micro instruction sets near the right end of the spectrum look very much like machine instruction sets. Okay, and yeah, in a latter case, the design is likely to fall near the right end of the spectrum. We can now deal with some of the terminology introduced. In essence, all of these pairs describe the same thing but emphasize different design characteristics. The degree of accuracy relates to the degree of identification between a given control task and specific microinstruction bits. As the bits become opaque, a given number of bits contain more information, so packing actually connotes encoding. And the term horizontal and vertical actually relate to the relative width of microinstructions. Okay. The terms hard and soft microprogramming are used to suggest the degree of closeness to the underlying control signals and hardware layout. Hard microprograms generally fixed and committed to read only memory. Soft microprograms are more changeable and are suggestive of user microprogram. Okay. The next is direct and versus indirect encoding. So actually, microprogram control unit are not designed using a pure and unencoded or horizontal microinstruction format. At least some degree of encoding is used to reduce control memory width and to simplify the task of microprogramming. So the basic techniques for encoding is illustrated as shown in this figure. Okay, so it's organized as a set of fields. Each field contains code, which upon decoding activates one or more control signals. So let's consider the implication. When the micro instruction is executed, the every field is decoded and generate control signals. And thus, with n fields, there are n simultaneous actions that are specified. And each action results in the activation of one or more control signals. But actually, it must be possible for each control signal to be activated by at least one field. Now let's consider individual field. Okay? A field consisting of L bits can contain one of codes, each of which can be encoded to be a different control signal parent. And because only one code can appear in a field at a time, then the codes are mutually exclusive, and the action they can cause also are mutually exclusive. So the design of an encoded microinstruction format can now be stated in simple terms. They organize the format into independent fields and define each field such that the alternative action that can be specified by a field are mutually exclusive. These 2 points are very important in the encoded microinstruction format. Okay. So two approaches can be taken to organizing the encoded microinstruction into fields which are functional and resource. With functional it identifies function within the machine and designates fields by function type. Okay. But resource encoding, it views the machine as consisting of a set of independent resources and defaults one field to each. Another aspect of encoding is whether it is direct or indirect, which is shown in the following figure. So with indirect encoding, one field is used to determine the interpretation of another field. But with uh, the direct one, then it's not that way. So actually, this technique generally implies two levels of decoding, and it will increase propagation delays. Yeah, we're done with today's lesson, and that's all for microprogramming. We will uh, discussing about control unit starting from next lesson, and then we will recap it all by yeah, showing you some architecture and how parallel processor to be built and some more advanced concept. Okay, and then we'll start to do some programming. Yippee, that's what you want, right? Okay, so here's a quote for you today. So Maya Angelou once said, if you don't like something, change it. If you can change it, change your attitude. Okay, so that's for today. I hope that you enjoy this video. Subscribe, give a like, comment, share this video. If you have any question, please let me know. If you have any critics, so please let me know too. Okay, so I'll be back every Monday, so keep watching my video. Goodbye.